keeps the channel, correct channel, so that's good. All right. So how was the homework assignment? Any questions about that one? I mean, okay, let me just kind of go to the homework assignment. We'll take a look at it and talk about the solution, and then we'll move on and talk a little more about Prolog today. All right, so the homework assignment is in discrete probability down here. And this one is, permutation or combination number 2. And this time, the only difference is this little part here. This was requirement of we can only go to the same destination once a year, okay? Which means once you go to Lake Tahoe in the summer, you cannot go to Lake Tahoe again in the winter, okay? Which also means that once you use up more destinations, then you have fewer options at the end or the later part of the year. But the ordering is still important, okay? Whether you go to Lake Tahoe first and then Hawaii, or Hawaii first and then go to Lake Tahoe, they're considered distinct because the airfare would be different, the cost of living over there will be different, and so on and so forth. So what do you think?
I got permutation.
Permutation is correct, okay? And how many are you choosing out of how many?
Choosing 5 out of 20.
Out of 5 out of 20. Okay, so the correct answer to this one is, the actual answer is the permutation of choosing 5 out of 20, which is also the same thing as 20 times 19 times blah, 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 all the way down to 6. That's the actual answer. Is that making any sense? Nope, I take it back. Never mind. Because we only have 5 destinations. So it's 18, 17, and 16. That is the actual answer. We don't have 15 time slots in the year, because the other answer is only it works when we have 15 time slots in a year. Since we only have 5 time slots of the year, for the first time slot we have all 20 choices. For the next time slot, we cannot reuse the same one as the first one, so we only get 19 choices. And then for the third one, we have used up 2 choices already, so we only have 18 choices left. So that's why it is a permutation problem and not a power problem like the previous one. Is that okay? All right, okay. All right, so with this out of the way, I am going to continue our discussion with Prolog, and today we're going to play with it a little bit too, okay? Because I think it doesn't hurt to actually see Prolog in action, performing queries and all kinds of fun stuff. So we do have a few more topics to finish before we can go ahead and play with Prolog. Let's see. Are there any questions from the discussion last time? Okay, so let's check out how far we went last time. And I think we went through substitution and also unification and also most general unification. So are there any questions about unification itself, which is a special kind of substitution that makes 2 well-formed formulae the same, okay? And then the most general unification is you cannot make it less specific anymore. Any less specific and it doesn't unify anymore. Is that part okay? I mean, are there any questions about these 2 last sections that we talked about on Monday? No questions? And are there any questions about the example that I use that is kind of like the reverse of unification? Remember, I presented several pieces of code that are copy, paste, and modify, and then go like, well, if these are all copy, paste, and modify, can we turn these into a subroutine so that we can just use parameters to handle the parts that are different, but we can maintain the rest being the same, so there's only one piece of code to maintain. Are there any questions about that part and how it relates to substitution? No questions? Okay, all right. So if there are any questions about this slide, just let me know, and we can always come back and revisit this particular slide. But since we don't have any current questions, we'll go ahead and take a look at the next slide, which is basically answering the question of how does Prolog work. Okay, so underneath Prolog, how does it work? But before we do this, let me just go ahead and give you an example of running Prolog. Okay, so we'll go ahead and first of all, we have to create a file with all the rules. Okay, so we'll create something that's simple first. So we don't want to start with something that's way too complex. So we'll say, test prolog 1. Okay, so this is my test file. And it's really just a text file to specify all the rules. And let's try something that is not even difficult. We'll try everything. We'll try something that are what they call as facts. Okay, so basically these are things that are just given to you as true. So we'll use something from our example from last time. Is a Jedi in parentheses, and I'll just say Obi-Wan. Okay, Obi-Wan is a Jedi. Is a Jedi. Luke Skywalker. Okay, so we'll just have these two rules in this particular example, and then we'll play with the Prolog engine just to see how do we load this file into Prolog, and then what kind of question can we ask Prolog to get some answers. And just to make it a little more fun, we can say is a cisp cds. Is that right, or did I misspell cds?
I think that's right.
I think that's right. Yeah.
You should make it lowercase to fit with the fact that Luke Skywalker is lowercase.
Yep. All the atoms of the universe, should be lowercase. Okay, so let's do this. And the Prolog engine that I use is called SWI Prolog. It is not a Linux-only type of interpretation engine. So if you look up SWI Prolog on the internet, you will find their website. It is open sourced. It's not a commercial product, but you can download it for just about any platform. So go to download and just kind of go to here. They have a daily build for Windows, but it's also available for all other operating systems. So you get the source code for Mac OS X, and then in Linux, they have their own packaging as well. So it is available for all platforms. For those of you who want to experiment, this is not a part of this class. I'm not going to ask you guys to write programs in Prolog in this class, but I just felt that, hey, some of you may be curious and want to kind of find out how to get it to work. Okay, so this is the command line version of it. When you want to load a file in, you just use open square bracket, and then the name of the file, which is testpl1 in this case. And I think you have to end with a period at the end. So it just says true, which means it's successful. Okay. So now these rules are in. Then we can start to ask questions. We can say, is a Jedi? Is Sidious a Jedi? Okay. There we go. And to answer the question, it says it's false. Okay. We cannot prove that Sidious is in fact a Jedi, and as a result, the answer to this question is false. Okay. Let's see if Obi-Wan is a Jedi. Is a Jedi Obi-Wan? And it is true. Yep, go ahead.
But then if you do not is a Jedi Sidious, would it give true then? Or would it give false?
Well, it's not, you cannot use a not here. Or maybe I got the syntax wrong. That's possible as well.
Actually, wait, I think
Well, we can go to tutorial and go to getting started. And when you execute a query, I think you can only use a predicate in a query. You cannot do anything else when you are making a query. Okay, then you can learn Prolog. And we have facts, rules, basically the same stuff that we have been talking about. So that in the syntax, we can now look at some simple examples. And I'm looking for how you specify negation. pretty sure I used the not as a negation in some of my examples already. Well, let's see. Well, we can test it with a different file.
There's a chapter 10 that cuts and negation.
There we go. The cut negation as failure. There we go. Okay, that's a fail here. Okay, here's a negate. Okay, so neg is the way to specify negation. So if I put it in the query, let's see if that will work here. Is a Jedi Sidious. Nope, it doesn't like neg. Oh, because negate here is actually a one of the predicates. But there's another way to ask questions too. You can also ask, who are the Jedis? So you can say, is a Jedi? And in here, you don't specify exactly who. You just specify, X with an underscore in front of it. Then it will say Obi-Wan. And if I press, I think the space key, it will display the next answer, and it would keep going like that. So it would actually look for all the possible answers to meet this particular goal, which can be handy, okay? Because if you want to maintain relationships like ancestry, who is the father of who is the mother of whom, and so on. So assuming you get the family tree entered correctly, and you also specify the rule of who's a descendant or who's an ancestor, you can have Prolog to answer the question of who are the descendants of X, Y, and Z. Because this way, because it can search and go through all the generations, and tell you who is whom's descendants. Is that making any sense? Okay. So how does it work? I mean, this is kind of mysterious in a way. Okay, so we can go ahead and define our test number 2. So in test number 2, we are actually going to specify the relationship between people. So we'll go ahead and say, let's see, father of and mother of, okay? So we'll say father of. So in this case, do we want to stay in the Star Wars universe or just in general? We can just do it in general, okay? So we can say Michael is the father of Jim, okay? We can say Jim is the father of Jamie. And then we can also express mother of if you want to. So we can say Jane is the mother of Jim. And Mary is the mother of Jamie. Okay? And we should go one more generation. Well, actually, we do have 2 generations now already. So we can actually express a few more descendants. Okay, so father of. So Michael is also the father of Join. And same thing here. Jane is also the mother of John. And then with Jim, we also have Pat. Okay, Pat is a descendant of Jim. And mother, in terms of mothers, Mary is also the mother of Pat. There we go. Okay, so now we have 2 generations of people. Jamie does not have any descendants. Okay. Yep, there we go. All right.
I think you misspelled the last Mary.
The Mary, last one. Oh, okay, Manny. Okay. All right. So these are facts. Okay. In other words, these are all given to be true, and now we can specify rules. Okay. So when we specify rules, we can now specify is a descendant of, okay, or is an ancestor of. Either way is fine. So is an ancestor of. Ancestor of. Okay. So now we have to use variables because I don't want to spell out all the possible answers, ancestor of within this particular hierarchy. So I'm going to use x and y to specify. Okay, is x the ancestor of y? Okay. Well, x is the ancestor of y only if the following things are all true. Okay. So we want to specify the simple stuff first, like if x is the father of y, well, technically x is an ancestor of y, even though it's just one generation. So we can say, okay, the simplest rule here is to say father of xy. So use the same exact variables. Now remember, in the previous class, we said that anything, all the variables that appear in the head of a rule, in other words, the left-hand side of this particular only if symbol, anything on this side, in this case x and y, they are universally quantified. In other words, give me any x and any y, okay? If x is the father of y, then x is also an ancestor of y. Well, what if they're not related using father of? Well, according to this rule, then they are not. X is not an ancestor of y. Then what about mother? Okay, how do we express the or in this case? Because if x is a mother of y, then x is also an ancestor of y. So the way to do that is to specify another rule, ancestor of xy, same head, and then we specify mother of in this case. So now it becomes, there are two alternatives now. Two alternatives to make x the ancestor of y. Okay, according to this, just for one generation purposes, you can say, x is the father of y, then x is an ancestor of y. Or if you can prove that x is the mother of y, then x is also an ancestor of y. Is that okay so far? Okay. But this is only one generation. So things get a little bit more fun when you say, okay, what about cross generation? So now you can say ancestor of, okay, xy. And this is where you can specify a free variable on the other side in the body that is basically implicitly using the existential quantifier. So in this case, you can say, okay, let's say that x is the father of z. Okay, so z is not appearing in the head, and as a result, z from the perspective of the body is quote unquote a free variable, which also means it is existential. Yep.
Couldn't you just use ancestor of and define it recursively, like ancestor of x, c,
Oh, well, we're getting there. We're getting there, because we want to specify something that's concrete first, and then we specify ancestor of. So now we can say ancestor. What if z is also an ancestor of y? So it's kind of transitive, right? Because in terms of relations, ancestry is transitive. If x is an ancestor of z and z is an ancestor of y, that makes x an ancestor of y. Is that okay? Yep.
But for the first one, we know that if father of x comma z, or if mother of x comma z, then ancestor of x comma z. So if we could just put ancestor of x comma z in the first one, then it would completely specify.
You've been changing this rule here to incorporate the ancestor of?
No. In the first part of ancestor of x comma y, if father of x comma z, because now you're going to have to write another one that says ancestor of x comma y if mother of x comma z. And I'm just wondering, would it work?
Oh, I see what you mean.
Also, like you wrote ancestor instead of ancestor of.
Oh, okay. So your idea is to change this one instead of father of, you use ancestor of.
Yeah, would that work? Because it feels to me like it would.
I'm just going through the engine here. It will work only if you want to prove specific cases, like whether a particular person is the ancestor of the other person. It will not work if you're looking for all descendants of a particular person, because it will lead to infinite recursion. It won't stop.
You could put not ancestor of if like ancestor of y comma x.
This is okay. Let's get back to another concept that we have talked about in this class, okay, which is proof by induction. Do you guys remember proof by induction? What are the two things that you need in a proof by induction?
Base case.
A base case, which is concrete, okay, and the induction step, which basically says if you can prove it up to case n minus 1, and if you assume case n minus 1 is true, then we'll go ahead and use that to prove case n. If that is possible, then your proof by induction is done. Do you remember that? Okay? So it's kind of like that here, because the way it is here is there's no base case, okay? Because we're using ancestor of to define ancestor of. Now, even though we do have these ancestor of over here, at the top, that does connect to the base cases, this one does not, okay? Which to us, it seems to make sense, okay? To us, this makes sense because, oh, okay, but this ancestor of can be instantiated using father of or mother of, and therefore it is resolvable. And once this is resolvable, we can deal with this one here. But when you're looking for all possible answers, which means, okay, tell me, Michael is the ancestor of, and then a variable, find me all the descendants of Michael, that gets a lot more difficult because now it doesn't know how to instantiate, it doesn't know which rule to use. But in this case, I guess it will still go for this rule first and instantiate that and then find out, the answer. But I guess we can give it a try, see if this works. So it might work, but only because of the ordering of the rules. So in Prolog, if I flip the order of the rules, if I take out these two and put it over here, then that for sure would not work. Because the way Prolog tries to satisfy the rules is always from top to bottom, and then for each rule is always from left to right. Okay, so if I define the rules like this, then we'll always try to use the first rule to prove something. And it just won't stop in this case. But if we flip it like what we had before, that might actually work. So we'll go ahead and find out whether this works or not. Okay, so we'll save the file and give it a try. SWI Prolog, and this is a test Prolog 2. And then we want to find ancestor of. The first one is Michael. We want to find all descendants of Michael. And then the variable for the descendant typically has an underscore in front of that to basically say this is from the query itself. So we'll press the enter key, Jim, John, Jamie, Pat, and out of local stack because it has infinite recursion. So that's why we don't want to specify rules like that.
All right.
Okay? Now, just because this one doesn't work doesn't mean the other one is going to work, right? Because they are not. So let's change this one. You can always define parent of. Okay, that's fine if you want to define parent of, and then we can make use of parent of in ancestor of. That will work. Okay, so instead of doing this, we can say parent of. So we take the gender part out of it. Okay, and in the ancestor of, we'll still need to rely on parent of here and not ancestor of. Yep.
You didn't put in ancestor of is parent of.
Right.
Without that little loop. Okay.
So you'll need this, right?
Why? Not Z. Because it's
Oh,
not
right.
defined.
There's Y over here. The evilness of copy, paste, and modify. Yeah. All right, so this will work. Okay, this will work because the rule of ancestor of, the one that is recursive, always start with something that is non-recursive, because parent of is not recursive. Parent of does not rely on parent of itself, because parent of only depends on father of and also mother of. But father of and mother of themselves are not recursive either. So that's when, so this one will work. I will be able to find all the descendants of Michael in this case. Okay, so save it and give it a try. Test prolog 2, and then we ask the question again. Ancestor of Michael and underscore x as the descendant. And it always returns false because we have, it will keep trying until it doesn't work anymore. So the answer, quote unquote, is always false in this case. On the other hand, if you ask specifically whether, let's say, Pat is a descendant of Michael, or whether Michael is an ancestor of Pat, then it will come back and say true. Because in this case, it will say true first and then say false, because it will first confirm that yes, the answer to that question is true, but then it won't stop the recursion until it fails. It's like, okay, we have found one case to make this particular answer true, but we won't stop. We'll keep going until there are no more choices to choose from. Is that okay or not? You can also do it the other way around. You can say, okay, tell me who are the ancestors of Pat. Okay, so we have these people being ancestors of Pat. Is that okay? All right. Now you can always restructure the original file or how you state the facts. So in other words, you can change the way you define parent of and also father of and mother of. Because you can also define gender. Okay, you can say he is male. Okay, Michael is female in parentheses Jane and so on. So you can basically have a bunch of facts stating the gender of the people, and then have another bunch of facts to state parenthood. Okay, and then you can define father of, mother of if that is important. But for ancestry purposes, the gender part is not important. So as a result, you don't need the gender part if that is what you want. So there are many ways to implement the same kind of logic here. It's just entirely up to you to decide, okay, how do I want to define that? Is that okay or not? So okay, so these are rules. Okay, these are all rules. These are basically special rules called facts. Okay, because they are not exactly a general rule. These guys do have a head, but not a body. And then when we go into the actual Prolog engine, so we say PL2 like that, and this time let's say we want to find all the ancestor of Jamie. Okay, so this is called a goal. Okay, so this one single predicate that we type inside Prolog interactively is called a goal. So when you press the enter key, the Prolog engine will try to meet this particular goal until it cannot find any further answers. Are there any questions about this? Yep.
Is there a way to use cuts to keep it from always having false?
Yes, a cut is basically the exclamation point, which means beyond this point, do not backtrack anymore. Okay. So yeah.
The false at the end is annoying, and if I remember correctly, there's something to do with cuts that helps with that.
I do not think the cut can deal with the false at the end, but the cut can basically say if you want to, you can find just one ancestor with a cut, but the cut operator cannot be used to get rid of the false at the end.
And the semicolon is or, right?
Semicolon can be used as an or, but you can also define the rule separately as an or, as an alternative. Okay. Any other questions? Yep.
Is there a type of real-world application which Prolog is good at handling, or?
That's a very good question. Yep.
I know one.
Okay, go ahead.
Have you ever heard of the game show Jeopardy?
Yeah.
Have you ever heard of the computer designed by IBM called Watson?
Yeah.
There was a computer designed by IBM called Watson, which was designed to play Jeopardy, and the entirety of Watson is written in Prolog. That's one of real-world applications. So, if you want,
I did not know that it was written in Prolog. So
well,
IBM.
majority of it.
Watson.
Like, it used Prolog, if I remember correctly.
There's a lot of C++ and
I
Prolog.
where?
Go down on what language is IBM Watson programmed in?
Oh, there we go.
Says there's a lot of
But that's not from IBM itself. So we don't know the credibility of this claim, right?
Java, C++.
Yep, most of the work on Watson was done in Java, but there's a lot of C++ and Prolog in there too. But there's a lot of there are no quantification here. Since in this class we talk about quantifiers, right? So all this is saying is there exists at least one line in C++.
I remember.
Yep.
Yeah, I was just told by like a guy who worked at IBM that that he was writing code in Prolog, and I don't remember the other company, but I remember there was another company that my friend worked at, and they did a lot of work in Prolog. And my friend initially, when she had first heard of Prolog, is like, "What the heck? Why would you ever use this?" But after that, she kind of grew to love it.
Well, Prolog is good for
AI.
goal seeking. It's good for specify the rules. But the rules have to be very, very concrete, right? These are all Boolean logic. It's not fuzzy at all. So if you can specify the rules, you can specify the relationship between the predicates, then Prolog is a very useful engine to find an answer to a question. Because it does do the recursion thing, and it also does backtracking, so we find all possible answers. Yep.
It's using research and natural language processing, if I remember.
Natural language processing is fuzzy. Okay, if you use Prolog to process natural language, then if you miss something in the grammar, then it won't be able to process it,
Yeah.
which may not be the best engine for processing natural
Why
language.
a lot of people use
Yeah.
it, that's okay.
But historically, okay, to answer that particular question, historically, Prolog and Lisp, these are the two artificial intelligence programming languages. But this is from the past, okay? So this is like in the 80s or from the 70s to, I would say, the mid-80s. The United States, have always been using Lisp as quote-unquote an AI programming language. And then elsewhere, mostly in Japan, they use Prolog as the main programming language for AI applications. But this is in the back in the 70s and the 80s, and after the 80s, AI kind of died. People found that we cannot really quite do what we set out to do using Lisp or Prolog because it's all symbolic processing, and you can only do so much in terms of artificial intelligence with symbolic processing. Why? Symbolic processing means it's all based on words, lexicons, and stuff like that, right? So what is the limitation of that type of AI? Because we are talking about AI in terms of being able to understand an editorial of a newspaper and be able to form counter arguments by understanding the argument itself. Then you formulate counter arguments and stuff like that. Yes.
Prolog and Lisp are very brittle. They don't really allow you to be fuzzy, like you said. They don't allow you to be fuzzy, which is why people use stuff like neural networks and which is basically just numerical.
You can't introduce fuzziness. Okay, you can introduce randomness and fuzziness using any programming language. But fundamentally speaking, there's one thing that symbolic processing cannot do. Okay, blue. Okay, out of the blue, I just said blue. Yes. So what is blue? Okay, to you, blue is
Oh, right.
So what is the first thing that pops in your mind? Did BLUE pop up in your mind first, or did the color blue pop up in your mind first?
Your shirt.
Well, I guess that is the case as well. Okay, but that's even better because when you say blue, or when you type blue, okay, in Prolog, it's nothing more than a lexicon or just a string, right, of sorts. It does not link blue to different hues of blue. Okay, I see another blue shirt over here. I see a backpack that has some blue in it. I see another blue over here. But they're all different hues of blue, but they're all blue to me, right? But to a computer, blue is nothing more than the ASCII code of lowercase b, followed immediately by the ASCII code of L, followed immediately by the ASCII code of U and E. Okay. So unless you link blue to something, okay, unless you say, okay, if the RGB is within this range, it is considered as blue, okay? Unless you specify a rule like that, blue has no meaning whatsoever. It's really just a word. So that's the limitation of symbolic AI, because eventually they become circular. It's kind of like trying to look up the meaning of a word using a dictionary when you have no real life experience with that particular thing. Eventually it just goes back to itself. There's no way for a dictionary to truly define the meaning of a word unless it is grounded at some point. It has to terminate with something that is not explainable using just words. Okay, it has to link to some experience of yours. It has to link to some sensation that you have, So it has to be grounded. So symbolic AI has that one weakness of not being able to hook up to anything that is non-symbolic. And that's why that whole branch, the entire branch of that part of AI just kind of died in the early 80s, early to mid 80s. It's just kind of started to go downhill. My own dissertation was actually on an AI topic, but it's a strong AI topic. We'll talk about that later on too. It's called state space search, or using the Dijkstra's algorithm is one for a much more restrictive, type of problem that I was trying to solve. But nonetheless, okay, that's another branch of AI. But the symbolic branch of AI basically died, pretty much in the 90s, and I can tell because both of the AI professors at UC Davis did not get tenured, which is a pretty clear indication that it wasn't going anywhere. They didn't get the money to run the labs and stuff like that, and that's a big determining factor of whether they can stay or not. So did I answer that question of yours?
Yeah.
Okay, so it's kind of it's useful and used a lot in a certain era, but now it is kind of limited to certain things that lends itself to symbolic processing. Okay, but I can see it coming back, because of big data. And also the amount of processing power that we do have these days, I can see Prolog and Lisp coming back, because now we have a lot more stuff to chew on. Okay, when you look at Amazon, okay, so you can look at relationship in Amazon. Okay, just think about online merchants. What type of data is already stored in the Amazon servers? Who bought what, right? Okay, but it's not just that, okay, because they track your browsing habits as well. Okay, you browse this item, you read this review, blah, 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 leading to the actual purchase of this item. Okay, or this item is in your cart, and then you look at the suggestions, and then you change your cart to buy something else. All of that stuff is being maintained as raw data. As raw data is not really going to help Amazon much. But on the other hand, if they can figure out the probabilities and also formulate rules based on the probabilities, then they can start to have then you can have commercial applications. Am I making any sense here? Because then you can use something like the rules that we have just specified, and just say, okay, if these are the things that this person has done and meet these requirements, then go ahead and suggest that item as well. So if you can specify those rules as just simple rules like what we have seen here, and just let the engine run by itself to find all the possible answers and sort it by relevancy, then you have a commercial application, because now you can start to push things to consumers or customers based on these rules that you have observed in real world. Yep.
Is that what Amazon does? 'Cause
Oh yeah.
when you buy an item, it says like people who bought this item also bought like similar or related. Like suppose you bought like the first novel in a book, then you like it would say like people who bought this item also bought like second. Third.
That is actually a very big part of online merchants these days. Being able to basically it's called data mining. So looking at all the things, all the logs that Amazon has already kept on their servers, what is the best way to utilize that in order to sell even more stuff to people? Yep.
But with Amazon, they don't really use things like Prolog. What they do on the back end is using modern machine learning techniques, which usually what Amazon and Netflix have been doing recently. The solution that won the Netflix challenge back in 2012-ish. Nowadays, the most popular tool is artificial neural networks, which have kind of made a comeback from the 90s, where people kind of abandoned artificial neural networks for support vector machines. However, with the advent of recurrent neural networks are now kings again. So
only for certain applications.
They're more used than SVMs nowadays for the majority, I think, based on people I've talked to, but that's okay.
Yep, there are different branches of AI. So as you said, one branch of AI is neural network. Now, neural network is also an interesting one because it's kind of it took over Lisp and Prolog as the quote unquote new AI, because with neural networks it can actually quote unquote incorporate data of any kind. Okay, you can train a computer to recognize a face. Okay, in other words, let's go ahead and collect 10,000 pictures. Okay, of faces, of which let's say 1,000 of those are mine. So what you do is you say, okay, here's a picture. Is it tag? Computer comes back and say, yes. You say no. Okay, move on to the next one. So you keep training the computer using these samples and saying, okay, this is a picture. Is it tag? Yes. No. Okay. So the computer will make adjustments every single time based on the feedback you give it. So over time, the neural networks, will basically form the necessary numbers. Okay, they're all numerical values, and eventually, when you present a picture that the AI engine has never seen before, okay, assuming you train it correctly, then there's a high reliability of being able to recognize who is tagged and who is not tagged. Okay, so that's kind of the essence of neural network is just that. Yep.
That reminded me, I think someone put out AI bot on Twitter, and people started like saying nasty stuff to it. Like they started saying the nasty stuff back.
That happens to Watson as well.
Oh, yeah.
Yeah. So if you look up Watson, okay, I know we are digressing even further. So if you look up Watson and Urban Dictionary, that is actually one of the things. You can just go ahead and look it up. So somebody exposed Watson to the Urban Dictionary, and then they started to use slangs, to answer the researchers. Just go ahead and read one of these articles. I'm not going to put it up on the web today, in class. But if you want to look it up, that's really interesting. Okay, it's really interesting. The thing about Watson is not only the fact that it has an engine to find the answer, but also it can also rank relevancy based on the context of the question, and that is the difficult part. Okay, because symbolic processing, searching is easy, but to find out how you should rank the search results based on the context is the hard part. Okay. That's also something that we are good at, and most computers are not good at that just yet. Okay. All right. So we got all of this stuff, and getting back to this part here is how does it work? So I'm going to skip all this stuff here. Okay, there's definitely a little CNF part, but Prolog really does not resolve using the CNF mechanism or resolution that we know of. The problem has to do with we like CNF and we like resolution when we talked about propositional logic because it guarantees termination. Okay, because every single time you apply resolution, you do end up with a new term, but the new term is going to have one fewer variable. So if you keep repeating this application of resolution, eventually you will end up with something that has either one variable or you have a contradiction. You can terminate, okay? But it doesn't work in Prolog, okay? And the reason why it doesn't work in Prolog has to do with unification. So when you unify, you can end up making new terms, along the way. So it doesn't guarantee termination anymore. And this is a pretty interesting example of how to use Prolog to figure out the factorial of a number. Okay, so these two lines of code is how you compute factorial using Prolog. So let's go ahead and just kind of check this out a little bit and see whether it makes sense or not. The first one is really just a fact, okay? This also relates very closely to proof by induction, okay? So we'll take a look at this, but from two different perspectives. The first perspective is, okay, this is predicate logic, this is Prolog, let's see what it means. The first one is easy. It simply means the factorial of 0 is 1. That's all it's saying, okay? It's a fact, okay? There's no particular reason other than, yes, I'm telling you that the factorial of 0 is 1. Okay, that's just given to us. So the next one becomes a more general rule. This is the head of that rule, which means n and f are they are implicitly using a universal quantifier. And obviously, in this case, you should not really give n or f any negative values. That wouldn't make any sense, right? So we are assuming that n is at least a natural number, and we are assuming f is probably a natural number as well. But nonetheless, these two are universally quantified, okay? And this is the body of that particular rule. Everything that is separated by a comma is using conjunction. Comma is basically conjunction in the rule. So let's take a look at these particular well-formed formula inside this particular rule. N is greater than 0. Okay, which is literally just saying, okay, is n greater than 0? Is that okay? All right. And then the next one is saying n1 is n minus 1. Now here it becomes kind of interesting because n1 is not a variable in the head. So this becomes a unbound variable, and as a result, it is existential. Okay, there exists an n1 such that it is n minus 1. Well, but if you tell factorial what n is, then n1 is really just 1 less than the value of n. So that's how we bind n1 based on the value of n itself. Is that okay? All right. And then we have more. This is the recursive part. So the recursive part is using n1, which is bound because of, it is n minus 1. And now we have f1, which is not bound because f1 is not one of the variables in the head. So f1 is unbound. So it becomes a new query. So now, instead of answering the question, in addition to answering the question of what is the factorial of n, we now have a new question of what is the factorial f1 of n1. So that becomes a new question. And as it becomes a new question, the first thing it will do is it will check the first rule. Okay, is this an easy one? Is n1 0? Oh man, it's not. Then it will go back to this rule, and then it will check out what is 2 less than our original n, and then 3 less than the original n, until n becomes 0. Then we use the first rule and say, oh, what is the factorial of 0? And then we'll backtrack. Okay, and when we backtrack back to this point, then we will have f1 resolved already. So after f1 is resolved to a particular value, then we can say f itself is n times f1. Is that okay? So this gives you the ability to find the factorial of a particular number, but it doesn't give you the ability to check whether a particular number or what is, okay, if I give it 120 as f, it won't be able to tell me that 120 is 5 factorial. It doesn't go backwards. Now, why doesn't it go backwards? What do you think it has to do in order to go backwards? Yep.
So you wanted to know, you wanted to write a program. I'm not entirely sure what your question is. I'm just asking.
The question is, if I specify these two rules, and I say, whose factorial is 120? Why do you think these two rules cannot really do it? For practical reasons, okay? In terms of theory, yes, we have stated the relationships fairly clearly and correctly. But from the practical standpoint, why is that really not possible?
You need to do a lot of divisions.
No, you don't have to do divisions. You have to do a lot of tests. That's the bottom line, okay? Because this rule here is correct, okay? Mathematically speaking, this is a correct rule to express a number and its factorial. But the problem is, if you give this rule the factorial, which is the f, in order to find what is n, what are the potential values of n? Where do I start?
1.
But why can't I start with 100? Or negative 100? Or the smallest value that can be represented as an integer?
It says n is greater than 0.
Okay, but there are a lot of numbers that are greater than 0. Which one should I start?
But you have to check how it processes it, but I'm pretty sure it starts with 1 and then goes to 2 and then goes to 3.
I don't know whether it does process it like that, because what about fractional numbers, real numbers? Okay, so I'm personally curious and see whether it goes backwards. I know it goes forward for sure. Okay, give it n, it will find the factorial. But give it the factorial, can it go back and find out whose factorial it is? So that's the question. So let's go ahead and try that one. Test PL3, and we'll go ahead and paste the content and give it a try. Yep.
I have a question. You usually use lim or actually just vi, but how come you use cat this time?
Sorry?
How come you used cat this time instead of vi?
Because whatever I need to paste is already in the buffer, and I don't want to mess up any indentation.
All right.
Yep.
Oh, it's a lot of-
Okay, I think it's called factorial. Let me just double check the name. Yep. Okay. So factorial 0, 1, it would just come back and say yes, true, because the factorial of 0 is in fact 1. Okay, no problem. So now we want to ask, let's find out what is 3's factorial. Okay, and it was just say the factorial of 3 is 6. Not a problem. Okay, so it did find the correct answer. Or I can say, okay, is the factorial of 3 120? And it'll come back and say it's not true, okay, because the factorial of 3 is not 120. So none of these is a problem. So now I say, okay, what is the factorial of 5? Just to be sure that it is in fact 120. I'm pretty sure it is. Yep. Okay. So it does know that the factorial of 5 is 120. So now I reverse the question. Whose factorial is 120? And it says, doop. It cannot reverse it. Okay. So the problem is not so much the rule that we specified. The problem has to do with the engine itself not being able to handle this particular case. Okay. So now, why can't it handle this particular case when we can clearly do something like this with the ancestry example? Find all the descendants of Michael, right? Why can't it find reverse and find whose factorial is 120? It has to do with, okay, so n being greater than 0 is already a problem, because we specify our goal as factorial underscore x comma 120. So underscore x is a variable. Is that okay? So n is now not resolving. N is unifying with underscore x, which remains as a variable. So the problem is we are now saying, okay, since it's a variable, what should I test first? Okay, what can make underscore x greater than 0? And here we have a problem. There are tons of numbers that can do this, and the Prolog engine just doesn't deal with this. Okay, if it is a relationship of something like this that's greater than 0, and you don't specify what you're testing, it's not going to test all possible numbers that can be represented in Prolog and say, oh, let's try 1, then let's try 1.1, then let's try 1.2, and then let's try something else, because it's just not practical to do it. Is that making any sense? Okay. So even though the rule itself is correct, okay, it doesn't work. It just won't work. Now, if you want Prolog to be able to solve that particular problem, then you kind of have to reverse the whole thing and go backwards. You basically go backwards and say, okay, f is n times f1, and we know what f is, okay, and see if we can go backwards. But even with that, you still end up with unresolved numbers, so you can't really go backwards that easily. Is that okay so far? Okay. So really, there are just some ways, some things that cannot be solved using Prolog, even though you specify the rules correctly. The magic of Prolog, or the ability to find all descendants of Michael, has to do with 1, recursion, and 2, backtracking, which is also a property of recursion. Okay. How many people have exposure to the term backtracking already at this point? Nobody? Sort of? Okay. Well, I can give you a very easy example of backtracking. You don't have to write it down, well, at least not now, because we're not quite at that point yet. Okay, so let's say we're dealing with a maze, okay, and we'll make it an interesting one, somewhat interesting one. So we can do this. Do this. Okay, so let's call this, a maze, and let's say you start from here. Okay, we'll label these particular cells: A, B, C, D, E, F, G, H, I. Okay, so we have a 3x3 matrix, which is a maze, and then by putting a wall under A and B, and putting a wall under E, and a wall to the left-hand side of H, or between G and H, I now have a quote-unquote maze. Okay, and I'm trying to find out. Okay, let's just try to go to every single cell. Okay, so I want an algorithm that guarantees to visit every single cell in this case. So the algorithm, we can use a recursive algorithm. So the recursive algorithm is basically just saying, for each junction, okay, explore all the possibilities, and then you keep doing it that way. So we start with the E. The next one we go to, you can choose D or F. Okay, so I'm going to use a graph to represent that. So you can go to D, and then later on you can go to F. Let's say you go to D first. Okay, from D you say, okay, where else can I go? I'm not going to go backwards, but I want to see if there are unexplored cells. So G is the next one, but G is a dead end, so you backtrack to D, then you backtrack to E and say, okay, are there anything else from E that I have not explored? We haven't explored F yet. So the order of visiting is 1, 2, 3, and then technically speaking, we go back to D, and then we go back to E, and then from E we explore a new possibility, F, so this is number 6, and then from F we have 2 ways to go. Let's say we just pick C first. So C is 7, and from C there are no options because I don't want to go back to F just yet. So I have to go to B, which is 8, and then we go to A, which is 9, A is number 9, and A is a dead end. So when you get to a dead end, you backtrack. In other words, when you run out of options, you go back to the previous one and see if there are any further options from an earlier point perspective. So from A, we go back to B, and then from B has no further options, so we backtrack one more step to C. So from C, we go like, oh, okay, we can actually go explore. Oh, C doesn't have an option either. It has to go back to F. So this is 12. From F, we say, oh, we have another option. We can go to I. So I is number 13. From I, we can go to H. H is a dead end, which is number 14. So we have to backtrack and say, okay, can we go somewhere else from I? Nope, I does not have any further choices. So we have to backtrack again to F. So this is 16. And then from F, we have now explored all possible branches from F. And as a result, we backtrack from F. So we go back to E as 17. So basically, except for the first node and also the endpoints, we visit every single cell twice. But this is the mechanism of backtracking. Backtracking is basically saying when you run out of options, we go back to the previous step and see if there are any further open options in the previous step. Is that okay? All right. So backtracking is the basic engine of Prolog. So in pseudocode, if I want to look at the logic to solve a goal in Prolog, then it is kind of like defining a procedure, which is quote unquote to answer the predicate. Is it true or is it false? Okay, and the predicate is separated into two parts. The first part is the name of the predicate, and the second part is the list of parameters to this particular predicate. Okay, there's a reason why it's separated. It will be clear later on. And then the first thing I do is to initialize a local variable success to false. Okay, so let's say we're not going to succeed. And then what you do is from top to bottom of how the rules are specified, for each rule R, we'll do the following. And then the first thing is, okay, this part is actually very important in terms of backtracking. So before we explore anything else, we make a copy. Okay, we make a clone of list of parameters as a copy of the original list of parameters because it's passed by reference. Okay, so we don't want to change the one that is given to us. And then what we do is we go through each rule, and we only pay attention to the rules where the head of the rule can unify with the predicate and the clone of list of parameters. In other words, if you ask ancestor of, in parentheses, Michael, under a comma, and then underscore x, okay, it will say, is this going to unify with parent of? No, because the predicate, they don't even have the same name, okay? So it will keep going down the list until it finds the definition of ancestor of as a rule, okay? And go like, okay, it might match this time. It will then try to unify Michael with x. That's okay. You can always go more specific. If you start with a variable, you can always resolve to an actual element of the universe. That's not a problem. And then the second one is unifying y with underscore something, underscore x. That's okay too. You can always substitute a variable with another variable. That's fine. So it does unify. If it does unify, then it has another local variable called result that is initialized to be true. And since we have found a rule to evaluate in this case, then you have to evaluate from left to right. And then for each item of the body of that rule, you want to do the following until it is false, okay, until result is known to be false. So what you do is you say, this is where the recursion is. So for each component of the body, you extract the predicate and you extract the parameters of that particular predicate and say, okay, now this becomes my sub-question. And then you do the recursion. Is that okay? But what if this recursion fails? What if the result of this recursion is a failure?
Then it returns false.
It returns false for this particular rule, and then you get out of here because it makes no sense if you are evaluating a particular rule in a body. As you go from left to right, if there's one part that is known to be false or there's no way to make it succeed, there's no meaning to go any further because in a conjunction, you only need one false to make the entire thing false, right? So that's why this loop is going to exit as soon as the result of one part is false. Then you go like, okay, I'm going to give up with this particular rule. And then you say success is success or result, okay? So anything that is false is not going to make success, it's not going to change success. So you go back to this loop here and say, okay, I'll go find another rule and see if I can make that work. So just keep going like this. And that's why it is recursive. And it's also anything that is recursive, unless you do something to it, is also inherently going to backtrack. Is that making any sense or not? Is that okay? All right. Okay. And also, there's also a link here for those of you who want to see how this thing expands. When you try to find the factorial of a number, This is a hyperlink. You can actually go to another page that describes, how Prolog works. So this is actually a pretty good picture of, trying to confirm that the factorial of 3 is 6. So what happens is when you first ask the question, this is the first goal of 3, 6, then it will say, okay, is 3 greater than 0? Not a problem. And then it will instantiate the unbound variable, which is n1 to 2, because in this case, 3 minus 1 does give us a specific value. And because the right-hand side of this has a specific value, we can now instantiate n1 to be 2. And since n1 now has a value, we can now say, okay, what is the factorial of 2? Because in this case, f1 is actually unbound. Then we'll go here, 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 go down here, 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 and then go down to here. So at this point, it will basically find what is the factorial of 0, and it will match the first rule. Then we'll go back and say, oh, the factorial of 0 is in fact 1. Then this 1 is going back to here and say the factorial of 1 is 1. But once we know the factorial of 1 is 1, oh, actually I forgot about this step. Once we know the factorial of 0 is 1, then the factorial of 1 is 1 times 1, which is 1. So this 1 becomes the answer. It goes back to this step here. This 1 becomes this 1 over here. And we use this 1 on this side and find out that the factorial of 2 is 2. This 2 goes back to here, because now we know the factorial of 2 is 2. And then we utilize that 2 over here, and then we say the factorial of 3 is 3 times 2, which is 6, and then that 6 gets back to here, and that's how we find the answer, that the factorial of 3 is 6. It doesn't really quite show backtracking, because in nowhere of this particular tree we encounter a real dead end, and say, nope, cannot make that true. Is that okay or not? All right. Just a few more things to point out in terms of a Prolog or predicate logic in general. When you look at Prolog, it really is dealing with CNF, except resolution does not really apply, unfortunately. The reason why every single rule in Prolog is a CNF is this. Okay. So when we specify x implies y, remember x is not the head, x is actually the body, and then y is the head of a Prolog rule. Okay, so x tends to be a larger part, and then x tends to be the smaller part. The y, in fact, always is just a single predicate. But the way to rewrite implication is to negate x, and then we say or y. Okay, and that part is just the definition of implication. But that also has some other meaning, because in general, in Prolog, the body is longer. Okay, the body usually has blah 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 and blah 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 and blah 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 implies the head, which is Q in this case. But when you use De Morgan's law, so I'm combining. Well, okay, the second line is only because of the definition of implication. Okay, so I convert the P1 and P2 and P3 to the negation of that, and then change implication to an or. And then the third step is actually just making use of De Morgan's law. Okay, we take the negation of a big, huge conjunction into the negation of the individual terms, and then use the or in between. But when you look at the final form, it is a CNF. Okay, so that's why in Prolog we are still kind of dealing with CNF, but it doesn't use resolution, because resolution doesn't help in the case of, oh, we can actually manufacture more and more things, as a part of the CNF. Then resolution loses its advantage, because there's no guarantee of termination anymore. So that's why we don't use resolution in Prolog, even though in concept, that's actually what we do. Are there any questions about how CNF is still in Prolog, except we don't use it? So in Prolog, as an implementation, it is really just using a recursive algorithm, or what is equivalent to this recursive algorithm. In practice, it is a little bit more complex, because we have a cut operator, which means at some point you say, okay, do not backtrack beyond this point. If it fails after this point, just fail the whole thing. Okay? Don't go back any further. And using pure recursion, you can't really quite say that, okay? Because you cannot just say, okay, you cannot just delete a part of the stack, the call stack, and just say, okay, well, suppose you can using throw and catch in exceptions, but as barring the use of throws and catch in exception handling, there's no quick and easy way to handle a cut. The other thing that is also hard to implement using a pure recursive algorithm is when you find an answer to the top level goal, Prolog would actually display the answer. And there's no easy way to integrate it into this logic here. To basically say, okay, we have finished the very last step to satisfy the top level goal. Let's go ahead and print out the answer. Okay, there's no easy way to do that in a recursive algorithm. There's probably a way to do it. It's just not easy at all. So typically, Prolog itself is not implemented in C or C++ or some underlying programming language as a recursive engine. It's usually using its own stack and not use a recursive algorithm. Are there any questions about Prolog? No questions? Okay, all right. So that's our last topic, in terms of predicate logic or predicate calculus. So now getting back to here, we'll just take a quick review of all the stuff that we have, talked about. So everything about, this part, functions, relations, cardinality, countability, we talked about all of that stuff. Propositional logic, predicate logic, proof techniques. We actually went through quite a few of these already, even though we didn't quite name it. We talked about contradiction, proof by contradiction. The other ones are kind of like just clarification of what does not work. Okay, so they're not actual proof techniques. We can go back to here, but the main part of this part here is really proof by contradiction. And then we talked about proof by contradiction and also proof by induction. Okay, direct proof is basically just going forward. Okay, which is what we use from early on in the semester, even though it didn't have a name. Proof by counterexample. Okay, what is proof by counterexample? That's an easy one. You have a theorem that says, okay, everything blah 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 should be blah blah blah, or they exist. Well, there exists is harder, but if your theorem says for all blah blah blah, this has to be true. What is a counterexample?
So it would be kind of like the opposite of a proof by negation, right? Where instead of assuming or
proof by contradiction.
Or proof by contradiction, where like you assume the theorem is true and you say like since and then if you provide a counterexample, then you say like the theorem can't be.
But what is a counterexample? Is an example is a particular case that makes the theorem
false. Or
false.
Like
Exactly. Yep, exactly. Because you just proved the theorem does not apply to all elements of a particular set. We talked about induction. Even though we did not actually have a slide for induction, it is actually buried in. Okay, how many people remember where we started to talk about induction? Go a little further. Does that help jar your memory? Okay, did we use proof by induction in Pascal's identity, or did we use it in the binomial theorem?
Yeah.
But which one? Did we use it on the first one, the second one, or both? We definitely use it, okay, in the section of discrete probability distribution. But which one did we use proof by induction?
I did the same.
Binomial theorem.
Binomial theorem is the one. Okay, so let's revisit. Okay, I'm just helping you guys to kind of revisit all this stuff here. Pascal's identity does not involve. This is not the one. This is not mine. This is mine. Okay, so Pascal's identity does not involve the use of proof by induction because it's really just doing these tricks with factorial and combination. it did not require the use of proof by induction. So it was not here, but it was in the next one. So when we went to the binomial theorem, that's when we introduced proof by induction. Okay, is that okay or not? But do you see how these things kind of have, there's a particular pattern that is recurring. Proof by induction, but we see proof by induction in anything that is recursive. We also see, induction in how we specify rules in Prolog. Is that making any sense? Now, there's one more thing about the proof by induction, and also in the context of Prolog that I want to show you. Nope, not Q. What is that one? SPL2, I think that's the one. Okay, there we go. So in this particular rule, okay, ancestor of xy requires that x being the parent of z, and then the z being the parent of y. Okay, so that's okay. What do you think is going to happen if I switch the order and I specify the ancestor z has to be the ancestor of y, and then x has to be the ancestor of z? What would happen? Let me just kind of write it so that this way you know what I'm talking about. And then we'll just pretend to be the Prolog engine and say, okay, would that make a difference? Or, it doesn't really matter. Okay, whichever order we want to specify would work out the same. Okay, so let's evaluate. Let me turn on the line numbers. Let's go ahead and compare line 14 to line 15. To us, it means exactly the same thing, right? The ordering, it does not matter, because when you look at the truth table, conjunction is commutative. However, from the perspective of the Prolog engine, it does make a difference. If you specify the rule the way we did using line 14, it's good. Because the first thing it wants to confirm is, oh, let's go ahead and find a descendant of x by using the parent of. The parent of is not recursive. So eventually it will either give up and say, x is not the father or the mother of anyone, and just come back and fail, and go like, okay, there's no answer to that question, fail. And then the whole thing would just fail the rule itself, and then just backtrack, right? Or you can find an actual child of x, and then we'll use that child of x to the second part of the ancestor of. So it's not gonna be endless. When you look at line 15, then we have a problem, because now I can say, tell me who's the ancestor of Michael is the ancestor of whom? Okay, so that's the question. Then the first thing we'll do is to say, let me go find somebody z, such that z is the ancestor of y. And then what is it going to do? This can only match to one of these two, right? It might fail this one, it might fail this one too. What if those two fail? It will get down to the third, it will fail 13. Remember 14 is not there anymore. So we'll go back to 15, and then it will do the recursion. It will lead to endless recursion. So the conclusion is, if instead of using line 15, if we use line 15 instead of line 14, then the rule does not work. It's kind of like reversing proof by induction. You basically do this induction step first, but you don't specify the base case. Is that making any sense? So it is, we see the shadow of proof by induction even when we specify rules in Prolog. All right, so getting back to our notes, are there any questions about these topics so far? So I did go out of order a little bit, because we were talking about probabilities, and then we went back to talk about predicate logic. Questions? New questions? So we are done with predicate logic. I haven't really found a really good way to ask questions about predicate logic yet, so we are not going to have any homework assignment for this weekend. The next thing we'll talk about, how about this? I let you guys choose. We can talk about recursion. Okay, so when we talk about recursion, it is more about talking about the time complexity of recursive algorithms. Okay, and also the master theorem, which also has to do with the complexity of a recursive algorithm. Or we can go ahead and talk about probability is a short one, so we can do that too. The probability slide has to do with mostly just conditional probability, the Bayes theorem and stuff like that. It's a pretty short and quick topic. Or we can also go ahead and talk about graphs and trees. In particular, when we talk about graphs, we will talk about Dijkstra's algorithm, which is a way to traverse a graph and basically solve problems. Find the shortest path between 2 points, that sort of thing. And these three, the ordering is not important. One does not really depend on the other. So what do you guys want to do next week, on Monday? Recursion? Okay. Any objection to recursion? Okay, so recursion it is. So what you want to do is to read some of these notes over the weekend, just to get familiarized with the big O notation, recurrence relations, and just kind of look at binary search as an example. Yep, question?
I read that in computer science algorithm classes we use graphs a lot.
Graphs can be used to represent a lot of things. And trees are really specialized graphs. It's just graphs where there's a special constraint of the connectivity of the nodes. So graph theory or graph algorithms are more general than tree algorithms in general. But tree algorithms, because you have all of these constraints, they can be a lot more efficient. Yep. So that's a good observation.
All graphs have spanning trees, and all trees are graphs. All connected graphs have spanning trees. Sorry.
Yep.
All connected simple graphs. If you want to